Okay then, this is the fun bit where we start looking at how you can make salts. And we're not talking about the salts that you put on your chips, although you should know that the scientific name for that is sodium chloride. We are going to look at how we make solutions in science that are called salts, and these result from a reaction taking place between an acid and a base. And we're going to explore first of all what we mean by that. Now at the bottom you will see that we have the pH scale, and this is something that you probably learned back in year 7, where we said that if you used universal indicator, you'd put it into a reaction, and if it went red, then it was a strong acid, and if it went purple, then it was a strong alkali, and we said that neutrals were greens, and you can see the scale at the bottom there. Acids dissolve in water to produce acidic solutions, and these contain hydrogen ions. The concentration of these ions determines the pH of an acid. The higher the concentration of hydrogen ions, the more strongly acidic the solution is, and the lower its pH. Acidic solutions have a pH less than 7. Pure water and other neutral substances have a pH of 7. Alkalis dissolve in water to produce alkaline solutions with a pH more than 7. So like I said, we use an indicator which changes colour depending on whether it's acidic solution or an alkaline solution. Litmus is also, it's like a yellowy coloured paper. We can use litmus paper, which is also an indicator, shows a sudden change in colour. It is red in acids and blue in alkalis. Litmus cannot show how acidic or alkaline a solution is, but universal indicator can. Universal indicator is a mixture of different indicators. Each one changes colour over a different pH range. This means the pH of the solution can be estimated using universal indicator paper or universal indicator solution. To estimate the pH of a solution, and we can only estimate it, a spot of the solution is put onto the piece of paper, the universal indicator paper. After around 30 seconds, the colour of the spot is matched to the indicator chart as shown below, and this shows the corresponding pH for each colour. Now, I've talked a lot so far about the pH scale, and I've talked about how we can test to see whether a substance is an acid or an alkali. What we need to do now is we need to work out what's going on when we start to mix different reactants together. A base is a substance that can neutralise an acid. The reaction between an acid and a base is called neutralisation, and this is as shown at the top. If a base is soluble in water, it is an alkali, and that's where the mix-up happens sometimes. So if a base is soluble in water, then it's an alkali. So this shows you that not all bases are alkalis. The pH changes when the acids and alkalis react together. For example, the pH decreases when an acid is added to an alkali. If enough acid is added, the pH decreases from above pH 7 to below pH 7. A salt and water are produced in neutralisation reactions, and remember I said the salt is the solution that's the product after the reaction. So a general word equation is if you had an acid plus a base, reaction takes place and you produce a salt and water. And you can see that reaction there. Now if you look, there's a second reaction. If you had an acid and you added it to a carbonate, for instance, you would still make a salt and water, but you would make another product. and that's carbon dioxide. And all I can say here is, whenever you see the name of the chemical, if you see it's got carbon in there at all, that should really raise an alarm bell that you are making carbon dioxide gas. Now, just on a side point, during one of your exams you may be asked how you can test for carbon dioxide gas. And what you would do there, because carbon dioxide is really heavy, is you could actually pour carbon dioxide into a solution of lime water, and the lime water will go cloudy or milky, and that's how you can tell carbon dioxide is present. So when it comes to naming salts, we always use these rules. Okay, what you need to do is you need to look at the name of the acid you are adding, whether it's your base or whether it's a carbonate or whether it's a metal oxide or whether it's a metal hydroxide. It doesn't matter, you are always looking at the name of the acid. So if you added hydrochloric acid, you would make a something chloride as your salt. Sulfuric acid would make a something sulfate. Now I'm saying something because it depends on what you are reacting, and I'll explain that in a minute. Nitric acid will make a something nitrate, and phosphoric acid will make a something phosphate. So what am I talking about there? So what I'm saying is, for instance, let's just say we added together copper oxide and hydrochloric acid. Okay, what we'd look at there is we'd be taking the name of the product, the element at the beginning. So where you've got copper oxide, we'd take the copper and we'd join that together. We're adding it with hydrochloric acid, so the copper would be removed from the oxide and it would join with part of the hydrochloric acid, so it become copper chloride and water. Okay, remember, every time we are making water. So if you had copper oxide with hydrochloric acid, you would make copper chloride plus water. If you had copper oxide and sulfuric acid, you would make copper sulfate and water. If you had copper oxide and nitric acid, you would make copper nitrate and water. And hopefully you've seen a pattern by now. If you added copper oxide to phosphoric acid, you would make copper phosphate plus water. Let's just change one of the reactants then. Okay, we're going to have a look at sodium hydroxide. Okay, so we've got sodium hydroxide plus hydrochloric acid. So we'd take the sodium and join that with the chloride to make the name of the salt. So if we had sodium hydroxide plus hydrochloric acid, we'd make sodium chloride plus water. If we had sodium hydroxide plus sulfuric acid, we'd make sodium sulfate plus water. If we had sodium hydroxide and mixed it with nitric acid, we'd have sodium nitrate plus water. If we had sodium hydroxide plus phosphoric acid, we'd make sodium phosphate plus water. Hopefully you're getting sick of me saying plus water, because that comes up every single time. Now let's just change it slightly and add in one of those carbonates that I talked about before. Let's just say we had calcium carbonate plus hydrochloric acid. It's exactly the same rules. You take the first element, calcium, so it'd be calcium chloride plus water, but this time it's plus carbon dioxide as well. If we had calcium carbonate and we joined it with sulfuric acid, we'd have calcium sulfate plus water. plus carbon dioxide. If we had calcium carbonate and we added that to nitric acid, we'd have calcium nitrate plus water plus carbon dioxide. If we had calcium carbonate plus phosphoric acid, we'd have calcium phosphate plus water plus carbon dioxide. So hopefully you can start to see a pattern emerging there. Okay, so that's what we're talking about. We've talked about neutralisation reactions, which can be summarised by looking at what happens to the ions. Alkalis in solution contain OH-, whereas acids in solution contain H+. And this is an ionic equation that you can learn, and that should be a little number 2 in the middle there, because that's showing you what's happening for a neutralisation process. So H plus OH minus will give you H2O, so basically water, which is what neutralisation is looking at. So universal indicator is used to determine the pH, as we've discussed, and bases are substances that are oxides or hydroxides of metals and have a pH greater than 7. Soluble bases are called alkalis, and that's the main importance. Like I said earlier, if they are soluble, they can be called alkalis. If they are not, then they are just a base. Now, I haven't covered on here balancing symbol equations. What I suggest is you go onto Frog and have a look at the textbook that is there for you to view, and have a look at the balancing equations there.